If you haven't heard, there's a thought experiment that's been captivating minds across the internet lately. Imagine traveling not at the speed of light, that's been done to death in science fiction, but at 1 light year per second. That's not a misspeak, not light speed, a light year per second. The difference between these two concepts is so staggering, so incomprehensibly vast, that it breaks nearly everything we understand about physics. And yet, exploring this impossibility reveals something profound about the universe we inhabit. Let me put this in perspective. Light travels at roughly 300,000 kilometers per second. That's fast enough to circle Earth's equator 7.5 times in a single second. It's the cosmic speed limit, the maximum velocity at which information, energy, or matter can move through space-time, according to Einstein's theory of relativity. Nothing with mass can reach this speed, let alone exceed it. And a light year? That's the distance light travels in an entire year, about 9.46 trillion kilometers. Now, imagine crossing that entire distance in just 1 second. You'd be traveling approximately 31.5 million times faster than light itself. This isn't just impossible. It's so far beyond impossible that it ventures into territory where our current physics simply stops making sense. Relativity tells us that as you approach light speed, time dilates, length contracts, and your mass would theoretically approach infinity. The energy required to accelerate you to light speed would also be infinite, but at a light year per second, we'd need to invent entirely new physics to even begin describing what would happen. This is a speed so extreme that you'd be covering distances in seconds that light itself takes years to traverse. But here's why this thought experiment matters. By exploring this impossible scenario, we can better understand the true scale of the cosmos. We can visualize cosmic distances in a way that makes them comprehensible to our earthbound minds. We can trace a journey through the universe that would take us from our solar neighborhood to the farthest reaches of the observable universe, all while contemplating what such speeds would mean for our perception of reality itself. So, what would you actually see if you could somehow travel at this incomprehensible velocity? What cosmic landmarks would flash past your viewport? How would the universe reveal itself to an observer moving at speeds that dwarf even light itself? Join me as we embark on an impossible journey across the cosmos, one that will take us through our solar system, past neighboring stars, across the Milky Way, through our local galactic neighborhood, and ultimately toward the very edge of the observable universe. This won't be a journey bound by the laws of physics as we understand them. Instead, it's an exercise in scale and perspective, a way to truly grasp just how vast the universe is and how even traveling millions of times faster than light, we'd still find ourselves humbled by cosmic distances. Along the way, we'll encounter wonders that would take light itself years, centuries, millennia, or even billions of years to reach, and we'll do it all in a time frame measured in seconds, minutes, and hours. The universe has been expanding for 13.8 billion years, growing larger with each passing moment. Galaxies drift apart, space itself stretches, and the observable universe now spans some 93 billion light-years in diameter. Even at our impossible speed of 1 light year per second, crossing the entire observable universe would take us roughly 2.95 billion seconds. That's about 93 years. Even at speeds that mock Einstein himself, the cosmos remains almost incomprehensibly vast. But that's getting ahead of ourselves. Before we venture into the depths of intergalactic space, we need to establish where we're starting from. We need to understand what we'd leave behind as we accelerate to this reality-breaking velocity. We need to see our cosmic neighborhood, the solar system, from a perspective that no human has ever truly experienced. Because even in our own stellar backyard, even in the small corner of space we call home, the distances are far greater than most people realize. And at 1 light year per second, we'd cross our entire solar system in a matter of moments. Are you ready? Then let's begin this impossible journey. Let's accelerate to 1 light year per second and see what the universe looks like when viewed at speeds that exist only in imagination. Let's discover what lies between us and the cosmic horizon, and in doing so, perhaps gain a deeper appreciation for both the vastness of space and the remarkable fact that we exist in it at all. Our journey begins on Earth, that pale blue dot suspended in a sunbeam, as Carl Sagan once described it. But we won't linger here long. The moment we accelerate to 1 light year per second, everything changes. Let me walk you through those first crucial moments as we leave our solar system behind. Light from the sun takes about 8 minutes and 20 seconds to reach Earth. That's the baseline by which we measure distances in our solar system. The time it takes for light, the fastest thing in the universe under normal physics, to traverse the space between our star and our world. At 1 light year per second, we'd cover that distance, 150 million kilometers, in a small fraction of a second. In fact, we'd traverse the distance from Earth to the Sun in roughly 0.000016 seconds. That's 16 millionths of a second. You'd barely have time to blink before the Sun, that massive nuclear furnace that has warmed our world for billions of years, becomes just another point of light behind us. But let's slow down our description, even if our speed remains constant, so we can appreciate what we're passing. In the first thousandth of a second of our journey, we've already left the inner solar system entirely behind. Earth, Venus, Mercury, all have receded to mere specks. These rocky worlds, the terrestrial planets that share our sun's inner neighborhood, vanish almost instantaneously. Mars, that rusty red world that humanity dreams of colonizing, the subject of countless missions and future aspirations, disappears from view almost instantly. The asteroid belt, that collection of rocky debris between Mars and Jupiter, represents no obstacle whatsoever. We pass through it so quickly that even if we were on a collision course with the largest asteroids, Ceres, Vesta, Pallas, we'd phase through their positions before any impact could occur. Within the first full second of travel, we've moved beyond Jupiter's orbit. That massive gas giant, with its swirling storms and numerous moons, exists behind us now. Jupiter, the king of planets, containing more mass than all the other planets combined, with its great red spot that could swallow multiple Earths, with its fascinating moons, Europa, Ganymede, Callisto, and Io, each a world unto itself, all of it recedes behind us in a single second. Saturn, with its magnificent rings of ice and rock, those breathtaking bands that have captivated astronomers since Galileo first glimpsed them through his primitive telescope, vanishes in our forward view in less than 2 seconds. In the same amount of time it takes you to say 1 light year per second, we've traveled beyond the orbit of Uranus, that tilted ice giant spinning on its side, its pale blue-green disk and faint rings nothing but a memory. Neptune, the outermost of the major planets, orbits the Sun at an average distance of about 4.5 billion kilometers, roughly 30 times Earth's distance from the Sun. This distant world, the last planet discovered in our solar system through mathematical prediction before being observed visually, takes 165 Earth years to complete a single orbit around the Sun. At our speed, we clear Neptune's orbit in about 5 seconds. 5 seconds. That's less time than it takes to microwave a cup of coffee, and we've crossed the entire realm of the major planets. We've traversed a region of space that took humanity's fastest spacecraft, Voyager 1, 12 years to cross. We've passed through a volume of space that contains virtually everything most people think of when they imagine our solar system. But the solar system doesn't end at Neptune. This is a common misconception. The realm of our sun's gravitational influence extends far beyond the orbit of the most distant planet. Beyond the ice giants lies the Kuiper Belt, a vast region of icy bodies, dwarf planets, and comets that extends from Neptune's orbit to approximately 50 astronomical units from the Sun. An astronomical unit, or AU, is the distance from Earth to the Sun, our fundamental measuring stick for solar system distances.
The Kuiper Belt is home to Pluto, that former ninth planet that was reclassified as a dwarf planet in 2006, along with Eris, Makemake, Haume, and countless other frozen worlds. This region, which light takes about 7 hours to cross, takes us roughly 9 seconds to traverse. These icy bodies are remnants from the formation of the solar system, pristine samples of the material from which the planets formed. They're composed largely of frozen water, methane, and ammonia with rocky cores. Some are quite large. Pluto itself is about 2,377 kilometers in diameter, roughly 2/3 the diameter of Earth's moon. The Kuiper Belt is also the source of many short-period comets, those icy wanderers that occasionally swing through the inner solar system, growing magnificent tails as the sun's heat vaporizes their ices. And still, we haven't left the solar system proper. Far beyond the Kuiper Belt lies the Oort cloud, a theoretical spherical shell of icy objects that extends perhaps halfway to the nearest star. This is the realm of long-period comets, those cosmic wanderers that occasionally dive towards the inner solar system on orbital paths that take thousands or even millions of years to complete. The Oort cloud is thought to extend to somewhere between 100,000 and 200,000 astronomical units from the Sun, roughly 2 light-years at its outer edge. This makes it by far the largest structure in our solar system, dwarfing everything interior to it. The Oort cloud has never been directly observed. Its existence is inferred from the orbits of long-period comets, which seem to originate from all directions in space, suggesting a spherical distribution of icy bodies surrounding the Sun. These objects are so distant and so faint that we can only see them when they're heated by the Sun during their rare passages through the inner solar system. But astronomical calculations suggest there could be trillions of icy bodies in the Oort cloud, with a total mass perhaps several times that of Earth. At 1 light-year per second, we'd cross the entire Oort cloud in about 2 to 4 seconds. Think about that for a moment. A region of space so vast that light itself would take 2 years to cross it. A region that defines the gravitational boundary of our solar system passes by in the time it takes you to exhale. In those few seconds, we transition from being creatures of our solar system to true interstellar travelers. We've left the Sun's domain and entered the space between the stars. As the Oort cloud fades behind us, the Sun itself begins to look different. No longer the blazing disk that dominates our sky from Earth, it now appears as an extraordinarily bright star, still the brightest star in the sky by far, but unmistakably stellar rather than solar. Size of sugar cube. It's a near-perfect vacuum, far better than anything we can create in laboratories on Earth, where even our best vacuum chambers contain billions of atoms per cubic centimeter. At human speeds, at rocket speeds, even at light speed, this space would seem endlessly vast, but at our impossible velocity, it's merely the prelude to the journey ahead. But even as we leave the Sun behind us, we're not yet at the nearest star. That would be Proxima Centauri, part of the Alpha Centauri system, located about 4.24 light-years away. At our speed, we'll reach it in just over 4 seconds. 4 seconds to cross a gulf that human spacecraft, moving at their fastest, would take tens of thousands of years to traverse. 4 seconds to reach a destination that represents humanity's nearest stellar neighbor, a journey that seems impossibly distant by any conventional measure. The fastest spacecraft ever launched, Voyager 1, is traveling at about 17 kilometers per second. It would take over 70,000 years to reach Proxima Centauri. At our speed, we'll do it in 4 heartbeats. The solar system, our cosmic cradle, now lies behind us. The Sun has become just another star in the vast stellar tapestry of the Milky Way. And ahead of us, the stars await, each one a sun in its own right, most of them with their own retinue of worlds orbiting in the darkness. This is where our journey truly begins, in the space between the stars, racing towards destinations that would take light itself years to reach, but which we'll visit in mere seconds. The scale is about to shift dramatically, and with it, our understanding of just how vast the universe truly is.
4.24 seconds after leaving Earth, we arrive at Proxima Centauri. This small red dwarf, the closest stellar neighbor to our sun, would take light over 4 years to reach. We've done it in the time it takes to take a deep breath. But what would we actually see as we approach and pass this star? Proxima Centauri is a flare star, prone to violent outbursts of radiation that would make any orbiting planets rather inhospitable to life as we know it. These flares can increase the star's brightness by several times within minutes, unleashing torrents of X-rays and ultraviolet radiation. Any atmosphere on a planet orbiting this star would be constantly battered by this energetic radiation, potentially stripping it away over millions of years. It's much smaller and cooler than our sun, only about 1/8 the sun's mass and producing a mere fraction of its light. In fact, Proxima Centauri is so dim that despite being our nearest stellar neighbor, it's invisible to the naked eye from Earth, requiring a telescope to observe. But it's accompanied by 2 larger stellar companions, Alpha Centauri A and B, which orbit each other in a binary dance. These stars, more similar to our sun in size and temperature, lie slightly farther away, about 4.37 light-years from Earth. Alpha Centauri A is slightly larger and brighter than our sun, while Alpha Centauri B is somewhat smaller. Together, they orbit their common center of mass every 80 years, sometimes approaching each other as closely as the distance between the Sun and Saturn, other times separating to distances comparable to the Sun-Neptune gap. We'd reach Alpha Centauri A and B in about 4.37 seconds. The entire Alpha Centauri system, humanity's nearest stellar neighbors, the stuff of science fiction dreams for generations, passes by in less time than it takes to tie your shoes. And already we're moving on to the next star. These stars have been the subject of countless stories about humanity's first interstellar voyage, the logical first destination for any civilization achieving interstellar travel. But at our speed, they're merely the first checkpoint in a much longer journey. At 5.96 light-years distant, Barnard's star comes next. We arrive in just under 6 seconds. This is another red dwarf, smaller and dimmer than Proxima Centauri, but notable for having one of the highest proper motions of any known star. It's moving across our line of sight faster than almost any other star visible from Earth. If we were watching from Earth with a powerful telescope, we'd see Barnard's star shift position noticeably over the course of a human lifetime. It moves across the sky at about 10 arcseconds per year, which means it shifts by the width of the full moon every 180 years. But at our speed, we barely register its motion before it's behind us. For decades, astronomers thought Barnard's star might harbor planets. In the 1960s, some believed they'd detected the gravitational wobble indicating the presence of planetary companions, though these detections were later proven false. More recently, in 2018, astronomers announced the discovery of a super-Earth orbiting Barnard's star, a cold world about 3 times Earth's mass, likely frozen and inhospitable, but a planet nonetheless. Red dwarfs like this one are now known to be common hosts for planets, making them increasingly interesting targets in the search for life beyond Earth. Wolf 359 arrives at the 7.86-second mark. This faint red dwarf gained pop culture fame as the site of a fictional battle in Star Trek, but its real significance lies in its nature as a typical low-mass star. Then Lalande 211885 at 8.29 seconds, another red dwarf, one of the brightest of its type visible from Earth's northern hemisphere. These stars, though individually faint, are the most numerous stars in our galaxy, making up roughly 75% of all stellar objects. Understanding them is crucial to understanding the galaxy as a whole. Sirius, the brightest star in Earth's night sky, appears before us at the 8.6-second mark. Sirius is actually a binary system, consisting of Sirius A, a bright main sequence star twice the mass of the Sun, and Sirius B, a white dwarf,
the dense collapsed core of what was once a larger star. White dwarfs are remarkable objects, packing roughly the mass of the Sun into a volume about the size of Earth. A teaspoon of white dwarf material would weigh several tons on Earth. The matter is so compressed that it exists in a state called electron-degenerate matter, where quantum mechanical pressure from electrons prevents further collapse. White dwarfs are the fate that awaits stars like our Sun, billions of years from now, after they've exhausted their nuclear fuel and shed their outer layers. Sirius B completed this transformation relatively recently in cosmic terms, perhaps 120 million years ago. Before its collapse, it would have been the more massive of the two stars in the system, possibly outshining Sirius A. Now it's a faint ember, visible only because it's so close to us and because we have telescopes capable of detecting it next to its brilliant companion. As we continue outward, stars begin to accumulate. Luyten 7268 at 8.73 seconds. This is actually a binary system of two red dwarfs orbiting each other, both flare stars, prone to sudden outbursts of radiation. Ross 154 at 9.68 seconds. Ross 2482 at 10.32 seconds. Each of these is a star system in its own right, many potentially harboring planets we haven't yet detected. Each represents a destination that by conventional understanding would require generations of travel to reach. The nearest stars have been the subject of proposals for interstellar missions, concepts like Breakthrough Starshot, which envisions sending tiny laser-powered probes to Alpha Centauri at perhaps 20% the speed of light, a journey that would still take 20 years. But for us, they're merely waypoints, ticking by at roughly 1-second intervals. By the time we reach the 15-second mark, we've passed more than a dozen star systems. Epsilon Eridani, a star slightly smaller and cooler than the Sun, known to have at least one planet and a substantial debris disk, marks our position at about 10.5 light-years from Earth. This is the kind of star that astrobiologists get excited about, roughly the same age as the Sun when life arose on Earth, with confirmed planets and the right conditions for rocky worlds to form. The debris disk around Epsilon Eridani suggests ongoing planet formation, or the presence of a planetary system still being shaped by collisions and gravitational interactions. It's younger than our solar system by several billion years, giving us a glimpse of what our own neighborhood might have looked like when Earth was newly formed.
At 20 seconds, we're nearly 20 light-years from home. The number of stars we've encountered has grown considerably. We've passed through regions of space containing stars of various types, red dwarfs, which are the most common type of star in the galaxy, Sun-like yellow dwarfs, the G-type stars like our own, orange K-type dwarfs, slightly smaller and cooler than the Sun, and even some larger, hotter stars. We've encountered binary systems where two stars orbit each other, triple star systems where three stars perform an intricate gravitational dance, and isolated stars wandering alone through the galactic night. The diversity of stellar types is striking. Some stars are burning hydrogen in their cores, fusing it into helium and releasing energy. These are main sequence stars, stable and long-lived. Others are in different stages of stellar evolution. Some may be approaching the end of their hydrogen burning phase, beginning to swell into red giants. Others, like the white dwarf companion of Sirius, have already completed their evolution, now cooling slowly over trillions of years. This is where we need to pause and consider something remarkable. In 20 seconds, we've traveled farther from Earth than light, moving at its maximum speed, could travel in 20 years. We've crossed distances that represent the entire horizon of early telescopic astronomy. When Galileo first turned his telescope to the heavens in the early 1600s, these stars were simply points of light, indistinguishable from the thousands of others visible to the naked eye.
He had no way of knowing how far away they were, no concept that each was a sun in its own right. Now we understand that each is a star, many with their own planetary systems, their own stories written in the language of physics and chemistry. Each represents a potential site for planets, for chemistry, perhaps even for life. By the time we reach 30 seconds, with 30 light years out, we've passed Vega, that bright bluish star that serves as one of the vertices of the summer triangle visible from Earth's northern hemisphere. Vega is about twice the mass of the Sun and much younger, only about 455 million years old compared to the Sun's 4.6 billion years. It's spinning so rapidly that it's noticeably flattened at its poles. Its equatorial radius is about 19% larger than its polar radius. This rapid rotation affects how we see the star. We happen to be viewing Vega nearly pole on, which makes it appear brighter and hotter than it would if we saw it edge on. Vega is surrounded by a disk of dust, likely the debris from collisions between asteroids or comets in a system still young and dynamically active. In about 12,000 years from now, due to Earth's axial precession, the slow wobble of our planet's rotation axis, Vega will become the northern pole star, taking over from Polaris. This precession has occurred throughout human history. When the ancient Egyptians were building the pyramids, the pole star was Thuban in the constellation Draco. At 45 seconds, we're approaching 50 light years from Earth. We've now crossed into a region of space where the stars become noticeably more numerous. This isn't because stars are actually clustered more densely here, but simply because as we travel farther from Earth, we encompass an ever larger volume of space. The number of stars within our traveled distance grows with the cube of that distance. Double the distance, and you've potentially encountered 8 times as many stars. This mathematical relationship means that even though stellar density remains roughly constant in our galactic neighborhood, the absolute number of stars we encounter increases dramatically as we extend our radius. By the 1-minute mark, we're 60 light years from home. We've passed through regions containing hundreds of stars. Some of these stars are known to have planets. Hot Jupiters hugging close to their parent stars, tidally locked worlds where one side perpetually faces the sun while the other remains in eternal darkness. Super-Earths, several times more massive than our world, planets that have no analog in our solar system. Gas giants orbiting at distances that would place them well beyond our asteroid belt, where they formed in the cold outer regions of their planetary systems. Each planetary system is unique, shaped by the particular conditions of its formation, the composition of the protoplanetary disk from which it formed, and the gravitational influences of its stellar neighbors. This is the stellar neighborhood, the local bubble of space within which we can begin to map individual stars with some precision. From Earth, astronomers have catalogued most of the stars within this range, measured their distances using parallax, the apparent shift in position as Earth orbits the Sun, and determined their basic properties. Parallax works well for nearby stars, where the shift is measurable, but becomes increasingly difficult for more distant objects. But even with our best telescopes and most sophisticated instruments, our knowledge of these stars is limited. We know their masses, their temperatures, their compositions from spectroscopic analysis. We know that many have planets, detected through various methods, the transit method, where planets block a tiny fraction of their star's light as they pass in front, the radial velocity method, where the gravitational tug of planets causes stars to wobble slightly, and direct imaging, though this remains challenging for only the largest planets orbiting far from their stars. But the details, whether those planets have atmospheres, whether they harbor water, whether any might support life, remain largely mysterious. We can make educated guesses based on a planet's size, mass, and distance from its star. We can estimate surface temperatures and atmospheric pressures. But we can't yet characterize most exoplanet atmospheres in detail, can't determine with certainty whether liquid water exists on their surfaces, can't detect the chemical signatures that might indicate biological activity. At our impossible speed, these stars flash past like lampposts on a highway. Each one deserves a lifetime of study, a career of observation and analysis. Each one might harbor worlds where, if we could slow down and look carefully, we might find something unexpected, perhaps even something extraordinary. But we're moving too fast. At 1 light year per second, the stellar neighborhood is just the opening act. The real journey lies ahead, deeper into the Milky Way, towards regions where individual stars begin to blur together into the grand structure of our galaxy. And that's where we're heading next.
At the 2-minute mark, 120 seconds into our journey, we're 120 light years from Earth. The solar neighborhood is now well behind us. The stars we're passing are no longer individually famous, no longer the named stars that appear in astronomy textbooks or star charts. Instead, they're cataloged by number and position, members of vast stellar surveys that have mapped millions of stars across the galaxy. This is where we begin to encounter the structure of the Milky Way itself. Our galaxy is a barred spiral galaxy, roughly 100,000 to 180,000 light-years in diameter, containing between 100 and 400 billion stars. That uncertainty range, 100 to 400 billion, reflects just how difficult it is to count stars in a galaxy from within that galaxy. Imagine trying to count all the trees in a forest while standing in the middle of it, unable to rise above the canopy. That's our situation with the Milky Way. The galaxy is shaped like a disk with a central bulge, and extending from that bulge are several spiral arms where star formation is most active. Our solar system sits roughly 26,000 light-years from the galactic center, positioned between 2 major spiral arms, the Sagittarius arm and the Perseus arm, in a smaller structure called the Orion spur, or Orion arm. As we continue outward, still roughly in the plane of the galactic disk, we're crossing through different regions of the galaxy, each with its own character. Some regions are rich in young, hot blue stars, massive stars that burn through their fuel quickly and will explode as supernovae within just a few million years. Other regions contain older, cooler, redder stars that have been burning steadily for billions of years. 5 minutes in, 300 seconds, we're 300 light-years out. We've crossed the local bubble, a region of interstellar space around 300 light-years across, characterized by unusually low density of gas and dust. This bubble was likely created by ancient supernovae explosions that cleared out the interstellar medium, leaving behind a cavity of hot, tenuous gas. We're now entering denser regions of space, where interstellar dust begins to accumulate, where nebulae, vast clouds of gas and dust, create the raw material for new star formation. At 10 minutes, we're 600 light-years from home. We're deep within the galactic disk now, in regions where the stars are more tightly packed than in our local neighborhood. If we could somehow slow down and look around, we'd see the Milky Way's disk stretching above and below us like a luminous highway, thick with stars and punctuated by dark lanes of dust that obscure the light from more distant stars. This is also where we begin to encounter open star clusters, loose associations of stars born from the same giant molecular cloud, still relatively young in cosmic terms, gravitationally bound, but slowly drifting apart over millions of years. The Pleiades, that familiar cluster visible to the naked eye from Earth, lies about 444 light-years away.
We'd reach it in about 7.5 minutes. If we passed through it, we'd see its 7 bright stars, the 7 sisters of mythology, revealed as members of a cluster containing hundreds of stars, all born roughly 100 million years ago, all moving through space together. Just 15 minutes, 900 seconds, we are approaching 1,000 light-years from Earth. This represents a scale where the light we see from these stars left them around the time the Byzantine Empire was falling, when Johannes Gutenberg was inventing his printing press, when the Renaissance was just beginning in Europe. The light from our sun would take 1,000 years to reach here, meaning that any civilization at this distance, looking at Earth with sufficiently powerful telescopes, would see our world as it was in the Middle Ages. At 20 minutes, we're at 1,200 light-years. We're now at distances where parallax measurements become extremely difficult, even for modern space telescopes. Beyond a few thousand light-years, direct distance measurements become nearly impossible, and astronomers must rely on other methods, comparing the apparent brightness of stars to their known absolute brightness, using the period luminosity relationship of variable stars, or employing other indirect techniques. 30 minutes in, 1,800 seconds, we've traveled 1,800 light-years. We're still within the galactic disk, but we've crossed a significant distance. The Earth would be completely invisible from here unless someone was looking for it with technology far beyond our current capabilities. The sun would be just another faint star among billions, unremarkable and easy to overlook. This is where the true scale of the Milky Way begins to reveal itself. At 45 minutes, we're at 2,700 light-years. At 1 hour, 3,600 seconds, we've traveled 3,600 light-years, and yet we've barely put a dent in the distance to the galactic center. Remember, the center lies about 26,000 light-years from Earth. At 1 light-year per second, reaching it would take us 26,000 seconds. That's just over 7 hours. But let's continue at our current trajectory, which takes us outward rather than toward the center. At 2 hours, we're 7,200 light-years from Earth. At 3 hours, 10,800 light-years. We're approaching the outer edges of the Orion Spur, the minor spiral arm structure where our solar system resides. Soon we'll cross into either the Perseus arm or the Sagittarius arm, depending on our exact direction of travel. After 4 hours, 14,400 seconds, we've traveled 14,400 light-years. We're now more than halfway to the opposite edge of the galactic disk from our starting point. The structure of the galaxy is becoming more apparent. If we could somehow view the Milky Way from outside, we'd see ourselves as a point of light having traversed a significant arc through the spiral structure. At 5 hours, we're 18,000 light-years out. At 6 hours, 21,600 light-years. After 7 hours, we've traveled 25,200 light-years, nearly the distance from Earth to the galactic center. If we were heading toward the center instead of outward, we'd be approaching that dense, luminous core where hundreds of billions of stars crowd together, where a supermassive black hole lurks, 4 million times the mass of the sun. But we're heading outward, and at 8 hours, 28,800 seconds, we've exceeded the distance from Earth to the galactic center. We're in the outer disk now, where stars become progressively less numerous. At 9 hours, we are 32,400 light-years. At 10 hours, 36,000 light-years. The galactic disk is thinning out around us. The bright spiral arms with their young massive stars are behind us now. We're in the realm of older stars, the thick disk population, stars that formed early in the galaxy's history. 11 hours in, we're approaching 40,000 light-years. At 12 hours, 43,200 light-years. We're now beyond the main stellar disk of the Milky Way, entering the region where the galactic halo begins, a spherical distribution of old stars and globular clusters that surrounds the disk like a diffuse sphere. After 13 hours, 46,800 seconds, we're at 46,800 light-years. The Milky Way's disk is now largely behind us, visible as a luminous band if we look back. At 14 hours, 50,400 light-years. At 15 hours, 54,000 light-years. We've crossed the main body of the Milky Way entirely. At 16 hours and 40 minutes, 60,000 seconds, we're well into the galactic halo. The journey through the Milky Way has taken us just under a day. In that time, we've crossed from our local stellar neighborhood, through the spiral arms and disk structure, and out into the halo. We've traversed the entire galactic disk, passing billions of stars, countless planetary systems, nebulae, star clusters, and all the rich structure that makes our galaxy so magnificent. And now, as we continue outward, we're leaving the Milky Way behind. The next phase of our journey takes us into intergalactic space, toward the other galaxies in our local group. And that's where things become even more interesting.
At 70,000 seconds, just over 19.5 hours, we're 70,000 light-years from Earth. The Milky Way is now noticeably behind us, its spiral structure visible in its entirety if we look back. But we're not alone out here. The Milky Way isn't an isolated galaxy drifting alone through the cosmos. It's part of a structure called the local group, a collection of more than 50 galaxies bound together by their mutual gravitational attraction. The local group is dominated by two large spiral galaxies, our Milky Way and the Andromeda Galaxy. These two massive structures, along with their satellite galaxies and a collection of smaller dwarf galaxies, make up a region of space roughly 10 million light-years across. At our speed of 1 light-year per second, crossing the entire local group would take about 10 million seconds. That's roughly 115 days. But we're not crossing the entire group. Instead, we're heading toward its most prominent member aside from the Milky Way, Andromeda itself. But before we reach Andromeda, we'll encounter several of the Milky Way's satellite galaxies. These are smaller galaxies that orbit the Milky Way, much as the Moon orbits Earth, held in place by gravity. The closest of these is the Canis Major dwarf galaxy, located about 25,000 light-years from Earth. We actually passed through this region about 7 hours ago, though we might not have noticed it as a distinct structure. It's being torn apart by the Milky Way's tidal forces, its stars strewn along our trajectory in a vast stellar stream. At about 22 hours into our journey, roughly 79,000 seconds, we're approaching 80,000 light-years. This is the distance to the Large Magellanic Cloud, one of the most prominent satellite galaxies of the Milky Way, visible as a diffuse patch in the southern sky from Earth. The Large Magellanic Cloud is an irregular galaxy, lacking the organized spiral structure of the Milky Way, but rich in star-forming regions and young bright stars. As we approach the Large Magellanic Cloud, we'd see it transform from a small, hazy patch into a vast collection of individual stars and nebulae. The Tarantula Nebula, one of the most active star-forming regions in the entire local group, would be particularly prominent, a vast cloud of gas and dust being illuminated by the intense radiation from newly formed massive stars. This single nebula is so large and luminous that if it were as close to us as the Orion Nebula, the nearest major star-forming region to Earth, it would cast shadows at night. The Large Magellanic Cloud is home to approximately 30 billion stars. It's irregular in shape, stretched and distorted by the Milky Way's gravitational pull.
In fact, the Milky Way is slowly consuming the Large Magellanic Cloud, stripping away its gas and stars over hundreds of millions of years. This is galactic cannibalism, and it's a common process in the universe. Large galaxies grow by consuming smaller neighbors. We pass through the Large Magellanic Cloud in a matter of seconds. At our speed, even a galaxy 30,000 light-years across is traversed in just 30,000 seconds, about 8.5 hours. But we're not stopping here. We're continuing outward toward Andromeda. After about 24 hours, or exactly 1 day, we've traveled 86,400 light-years from Earth. We're well clear of the Milky Way's immediate vicinity now. The Small Magellanic Cloud, another satellite galaxy, lies about 200,000 light-years from Earth. We'd reach it at around 200,000 seconds, about 2.25 days into our journey. The Small Magellanic Cloud is smaller and less massive than its large companion, containing only a few billion stars. Like the Large Magellanic Cloud, it's being disrupted by the Milky Way's gravity. These two Magellanic Clouds are actually connected by a bridge of gas and stars, evidence of their gravitational interaction with each other and with the Milky Way. As we continue beyond the Magellanic Clouds, intergalactic space opens up around us. This is the void between galaxies, even emptier than interstellar space. The density of matter here drops to levels almost unimaginable, perhaps a handful of atoms per cubic meter, sometimes less. This is space in its purest form, vast expanses of near nothingness, with the occasional wisp of gas that was either ejected from galaxies by stellar winds and supernovae, or is primordial material left over from the Big Bang itself. In 3 days, we're 259,200 light-years from Earth. We've left the Milky Way and its immediate satellites far behind. Other galaxies in the local group begin to appear. Triangulum, the third largest galaxy in the local group, lies about 2.73 million light-years from Earth. We'd reach it in roughly 2.73 million seconds, about 31.5 days. Triangulum is another spiral galaxy, smaller than both the Milky Way and Andromeda, but still substantial, containing perhaps 40 billion stars. It has a more open spiral structure than either of its larger neighbors, and it's rich in regions of active star formation. Like the Milky Way and Andromeda, Triangulum has its own retinue of satellite galaxies, smaller dwarf galaxies bound by its gravity. But the main destination in the local group is Andromeda, also known as M31. It lies approximately 2.537 million light-years from Earth. At our speed, we'd reach Andromeda in about 2.537 million seconds, roughly 29.5 days after leaving Earth. As we approach Andromeda, it would gradually grow larger in our field of view. From Earth, Andromeda appears as a faint, elongated smudge, but that appearance is deceptive. Andromeda is actually enormous. If it were brighter, it would appear 6 times wider than the full moon in our sky. Its disk spans about 220,000 light-years, making it larger than the Milky Way. It contains perhaps 1 trillion stars, more than twice the stellar population of our own galaxy. Andromeda is a spiral galaxy, similar in overall structure to the Milky Way, but larger and more massive. It has a prominent central bulge, home to older stars, and spectacular spiral arms traced by young blue stars and bright nebulae. As we approach, we'd see these arms resolve into individual stars and star-forming regions, much as we saw the structure of the Milky Way resolve into detail during our earlier passage. Remarkably, Andromeda and the Milky Way are approaching each other. They're not moving apart as galaxies generally do in our expanding universe. Instead, they're on a collision course, drawn together by their mutual gravity. In about 4.5 billion years, these two galaxies will merge, their stars intermingling, though individual stellar collisions will be exceedingly rare given the vast distances between stars. and their supermassive black holes eventually combining. The resulting galaxy, sometimes nicknamed Milkomeda, will be a giant elliptical galaxy, quite different in structure from either of its progenitors. At 1 month, roughly 30 days, we've traveled about 2.6 million light-years, placing us near or within Andromeda. The local group's 2 largest galaxies are now within our traveled distance. But the local group extends beyond these giants. There are dozens of dwarf galaxies scattered throughout the group, small collections of stars that orbit the larger spirals or drift independently through the group's gravitational realm. At 40 days, we're about 3.5 million light-years. At 50 days, 4.3 million light-years. We're now crossing through the outer reaches of the local group. The dwarf galaxies become more dispersed here, the distances between them growing. At 60 days, 5.2 million light-years, we're approaching the edge of what's typically defined as the local group. At around 90 days, we've traveled 7.8 million light-years. We're now leaving the local group behind us. The Milky Way, Andromeda, Triangulum, and all their satellites are receding behind us. And ahead, a vast expanse of intergalactic space stretches out, and beyond that, other groups and clusters of galaxies await. The local group is just one small structure in a much larger cosmic web, and that's where our journey takes us next.
At 100 days, 8.64 million light-years from Earth, the local group is now behind us, visible if we look back as a small collection of luminous patches against the cosmic dark. The Milky Way and Andromeda, those 2 great spiral galaxies that dominate our local neighborhood, appear as distant smudges, their spiral structures no longer visible as distinct features, but rather as diffuse glows in the darkness. The Triangulum galaxy, the 3rd major member of our group, is barely distinguishable. The dwarf galaxies that orbit these larger structures, the Magellanic Clouds, the numerous satellite galaxies of Andromeda and the Milky Way, have faded from view entirely, their light too faint to distinguish at this distance. But we're not entering a true void. The universe, on large scales, is organized into a structure called the cosmic web, a vast network of galaxy filaments, sheets, walls, and voids that stretches across the observable universe. This structure emerged from the initial conditions of the Big Bang, from quantum fluctuations in the density of matter that were stretched to cosmic scales during the period of inflation in the universe's first fraction of a second. These tiny variations in density preserved in the cosmic microwave background as temperature fluctuations of only a few parts per 100,000 were the seeds from which all cosmic structure grew. The local group is part of a structure called the local sheet, a flat distribution of galaxies that includes not only our own group, but several other nearby galaxy groups as well. Imagine a wall or sheet of galaxies, a 2-dimensional surface embedded in 3-dimensional space, with galaxy groups scattered along this surface like cities along a coastline. This sheet is roughly perpendicular to another large structure, and together they form part of an even larger organization of matter. Understanding this hierarchy, from individual galaxies to groups to sheets to superclusters, is essential for grasping how the universe is structured on the largest scales. The cosmic web isn't a static structure. It's dynamic, constantly evolving under the influence of gravity. Dense regions attract more matter, becoming denser still. Galaxy groups slowly merge to form clusters. Clusters themselves can merge to form even larger structures. Meanwhile, the voids, those vast empty regions between the filaments and sheets, continue to expand, pushed outward by the gravitational attraction of the denser regions surrounding them. On the very largest scales, the expansion of the universe itself plays a role, with the most distant structures receding from each other as space expands.
Beyond the local group, the nearest significant concentration of galaxies is the Sculptor group, located about 11.4 million light-years away. We'd reach it at approximately 132 days into our journey. The Sculptor group is named after the constellation Sculptor, in whose direction it appears from Earth, a faint constellation in the southern sky, not particularly remarkable to the naked eye, but one that happens to lie in the same direction as this collection of galaxies. It contains several spiral galaxies and dwarf galaxies, the brightest of which is NGC 253, sometimes called the Silver Coin Galaxy, due to its appearance in telescopes. NGC 253 is a beautiful spiral galaxy, seen nearly edge-on from our perspective. It's a starburst galaxy, undergoing an episode of intense star formation in its central regions, producing stars at a rate much higher than in normal galaxies like the Milky Way. This burst of activity is likely triggered by gas being funneled toward the galactic center, possibly as a result of gravitational interactions with other galaxies in the group. The result is a brilliant core region filled with young hot stars and glowing nebulae where new stars are being born. As we pass through the Sculptor group, we'd notice that it's similar in overall structure to the local group, a collection of galaxies bound by gravity, dominated by a few larger spirals with numerous smaller companions. This seems to be a common pattern in the universe. Galaxies rarely exist in complete isolation. They tend to cluster together in groups and larger structures. The reason is fundamentally gravitational. Galaxies formed in regions of higher than average density in the early universe, and these same regions attracted other galaxies. Over billions of years, these collections of galaxies became gravitationally bound, forming the groups we observe today. The dynamics within these groups are complex and fascinating. Galaxies within a group are moving relative to each other, some approaching, others receding, all under the influence of their mutual gravity and the gravity of the dark matter that pervades the group. Sometimes galaxies pass close enough to interact gravitationally, distorting each other's shapes, triggering bursts of star formation, or even merging completely over hundreds of millions of years. These interactions shape the evolution of galaxies, transforming spirals into ellipticals, stripping away gas needed for star formation, and feeding the supermassive black holes at galactic centers.
At about 150 days, we're at 13 million light-years from Earth. We're passing through regions containing several galaxy groups. The Maffei group lies in this general vicinity, though it's difficult to observe from Earth because it's located behind the plane of our own Milky Way, obscured by dust and stars in the foreground. This is what astronomers call the zone of avoidance, a region of the sky where our view of the distant universe is blocked by our own galaxy. The dust in the Milky Way's disk absorbs visible light, making it difficult or impossible to see what lies beyond. Only in recent decades, with infrared and radio observations that can penetrate the dust, have we begun to map the galaxies hidden in this zone. The IC 342 Maffei group, as it's sometimes called, contains at least 10 galaxies, possibly more that remain hidden by the Milky Way's interference. IC 342 itself is a large spiral galaxy, one that would be much more prominent in our sky if it weren't obscured by intervening dust. Maffei 1 is a giant elliptical galaxy, while Maffei 2 is another spiral. These galaxies are gravitationally bound to each other, forming a group comparable in mass and structure to our own local group, but one that remained largely hidden from astronomers until relatively recently. Within 200 days, we've traveled 17.3 million light-years. The M81 group comes into view. This is a relatively nearby group containing the large spiral galaxy M81, also known as Bode's galaxy, along with M82, the Cigar galaxy, and several other members. The M81 group has been studied extensively because it's close enough for detailed observations, yet contains a rich variety of galaxy types and demonstrates many of the processes that shape galaxy evolution. M81 is particularly beautiful, a grand design spiral galaxy with well-defined arms curling out from a bright central bulge. The spiral arms are traced by young blue stars and glowing pink nebulae where star formation is occurring. These regions are where the galaxy's density wave, a pattern that rotates through the galactic disk, compresses gas and triggers star formation. The result is an elegant, organized structure that reveals the underlying dynamics of how spiral galaxies maintain their form over hundreds of millions of years. M82, by contrast, is undergoing a burst of intense star formation, likely triggered by a gravitational interaction with M81 millions of years ago. When M82 passed close to M81, tidal forces, the differential pull of gravity across M82's structure, compressed gas clouds and triggered widespread star formation. The star formation is so vigorous that it's driving a galactic wind, a flow of gas being expelled from the galaxy by the combined radiation and stellar winds from thousands of young, massive stars. This wind is visible in various wavelengths, from X-rays produced by hot gas to radio emissions from relativistic particles, and it's carrying gas out of M82 at velocities of hundreds of kilometers per second. The M81 group also contains NGC 3077, another starburst galaxy showing signs of interaction, and numerous dwarf galaxies. Tidal streams of hydrogen gas connect some of these galaxies, evidence of their gravitational interactions. These streams are like cosmic breadcrumbs, revealing the paths galaxies have taken through the group and the encounters they've experienced. By mapping these streams and modeling the dynamics of the group, astronomers can reconstruct its history and predict its future evolution. As we proceed, galaxy groups accumulate. At 250 days, we're at about 21.6 million light-years. At 300 days, we're approaching 26 million light-years. We're now traveling through a region rich in galaxy groups, all part of the broader structure of the local sheet and its neighboring structures. Each group contains anywhere from a handful to a few dozen galaxies, each galaxy potentially containing billions to hundreds of billions of stars. The total number of stars in even a modest galaxy group can reach into the trillions, and when we consider that many of those stars likely host planetary systems, the number of worlds becomes truly astronomical. At this scale, we begin to see patterns in the distribution of galaxies. They're not randomly scattered through space, but follow the structure of the cosmic web. Dense filaments and sheets are populated with galaxy groups, while vast voids contain relatively few galaxies. This structure reflects the distribution of both normal matter, the atoms that make up stars, gas, and planets, and dark matter, that mysterious substance that makes up about 85% of the matter in the universe but doesn't emit or absorb light. Dark matter's gravitational influence shapes the cosmic web. The filaments of the web are threaded with dark matter, and galaxy groups form where these filaments intersect. Dark matter provides the gravitational scaffolding on which normal matter accumulates, the framework that determines where galaxies form and how they're distributed through space. Without dark matter, the universe would look completely different. Galaxies wouldn't have formed as quickly or in the same patterns, and the large-scale structure we observe wouldn't exist. In 1 year, 365 days, we've traveled 31.5 million light-years. This is a significant milestone. In 1 year of travel at our impossible speed, we've covered a distance that light would take 31.5 million years to traverse. Think about that for a moment. The light we'd see from galaxies at this distance left them 31.5 million years ago during the Oligocene epoch on Earth, when early primates were evolving, when the first grasses were spreading across the continents, when the Earth's climate was cooling toward the ice ages that would define the Pleistocene. We've crossed through the local group and several neighboring groups, and we're approaching the outer boundaries of what's considered our local galactic neighborhood. Behind us lie dozens of galaxy groups, thousands of individual galaxies, and literally trillions of stars. We've traversed a volume of space large enough to contain a significant fraction of the local sheet's galaxies, and we've seen firsthand how galaxies organize themselves into groups, how these groups interact and evolve, and how the cosmic web structures matter on the largest observable scales. But this is only the beginning. The universe is organized on scales far larger than what we've encountered so far. All of these galaxy groups, the local group, the sculptor group, the M81 group, the IC342 Maffei group, and dozens of others, are themselves part of a much larger structure called the Virgo supercluster, also known as the local supercluster. This is a gravitationally bound collection of galaxy clusters and groups stretching across more than 100 million light-years, containing tens of thousands of galaxies, and anchored by the massive Virgo cluster at its center. And that's our next destination.
420 days into our journey, roughly 14 months, we've traveled 36.3 million light-years. We're now entering the influence of the Virgo cluster, the dominant gravitational center of our local supercluster. This is where the scale of cosmic structure truly begins to reveal itself. Up until this point, we've been traveling through relatively sparse regions of space, encountering galaxy groups that are loosely organized and separated by vast distances. But now we're approaching something fundamentally different, a true galaxy cluster, where thousands of galaxies crowd together in a volume of space not much larger than what we've already traversed. The Virgo cluster is an enormous concentration of galaxies located approximately 53 to 54 million light-years from Earth. At our speed, we'd reach its core in about 54 million seconds, roughly 625 days, or about 1 year and 8.5 months. But we'd begin to encounter outlying members of the cluster well before reaching its center. The gravitational influence of the Virgo cluster extends far beyond its visible boundaries, affecting galaxies hundreds of millions of light-years away, including our own local group. Unlike the galaxy groups we've passed through, which typically contain a few dozen galaxies at most, the Virgo cluster contains between 1,300 and 2,000 galaxies. This is a true galaxy cluster, a massive gravitational well where galaxies swarm like bees around a hive. The total mass of the Virgo cluster is estimated at about 1.2 quadrillion times the mass of the Sun. That's 1.2 followed by 15 zeros, a number so large it becomes almost meaningless. To put it in perspective, if the Sun were represented by a single grain of sand, the Virgo cluster would be represented by all the beaches on Earth combined, with room to spare. Most of that mass isn't in the form of stars, but rather dark matter, that mysterious, invisible substance that makes up roughly 85% of the matter in the universe, but doesn't emit, absorb, or reflect light. We know dark matter exists because we can see its gravitational effects. Galaxies in the Virgo cluster move too fast for the visible matter alone to hold them together. They'd fly apart unless some additional mass were present. That additional mass is dark matter, forming an invisible halo around and throughout the cluster, providing the gravitational glue that keeps thousands of galaxies bound together.
As we approach the Virgo cluster, the density of galaxies increases noticeably. 500 days in, we're beginning to see the cluster's outlying members. These are galaxies caught in the Virgo cluster's gravitational field, slowly falling inward, their motions dominated not by the expansion of the universe, but by the cluster's enormous mass. Some of these galaxies are in the process of being transformed by their environment. As they fall into the cluster, they encounter a hot, tenuous gas that fills the space between galaxies, the intracluster medium. This gas is extraordinarily hot, millions of degrees, heated by the gravitational energy released as the cluster formed, and by energy from supernova explosions and active galactic nuclei. When a galaxy moves through this hot gas, a process called ram pressure stripping can occur. The pressure of the gas strips away the galaxy's own gas, the raw material for star formation, much like wind strips leaves from a tree. Galaxies that fall into clusters often stop forming stars as a result, their gas reservoirs depleted by this stripping process. Over time, they transform from blue star-forming spirals into red quiescent galaxies with little ongoing stellar birth. At 550 days, we're at about 47.5 million light-years. The number of galaxies visible ahead is increasing dramatically. Where previously we might have encountered a few galaxies every million light-years, we're now seeing dozens, then hundreds as we approach the cluster's core. These aren't all the same type of galaxy. The cluster contains spirals like our Milky Way, but it's dominated by elliptical galaxies, smooth, featureless collections of stars with little ongoing star formation. Elliptical galaxies often form through galaxy mergers, and in a dense environment like a galaxy cluster, such mergers are common. In fact, we can observe galaxies in various stages of interaction and merger. Some show tidal tails, long streams of stars pulled out by gravitational forces during a close encounter. Others are clearly in the process of merging, their nuclei visible as separate bright spots within a distorted envelope of stars. These mergers are violent events on cosmic timescales, but to us, passing through at our impossible speed, they're frozen tableaus, snapshots of galactic evolution caught mid-process. After 600 days, we're approaching 52 million light-years. At 625 days, we reach the heart of the Virgo cluster. The giant elliptical galaxy M87 dominates the scene. This is one of the most massive galaxies in the local universe, containing perhaps several trillion stars. It's a monstrous object, with a total mass estimated at around 2.4 trillion times the mass of the Sun, including its extended halo of dark matter. If we could see M87's full extent, including its faint outer regions and the thousands of globular clusters that orbit it, it would span a region of space over 1.5 million light-years across. But M87 is famous for something else, its supermassive black hole. In 2019, the Event Horizon Telescope collaboration released the first ever image of a black hole, or rather, the shadow of a black hole against the glowing accretion disk of superheated matter swirling around it. That black hole was M87's central black hole, an object with a mass 6.5 billion times that of the Sun. The event horizon, the point of no return beyond which nothing can escape, has a diameter of about 38 billion kilometers, roughly 2.5 times the size of Neptune's orbit. This is an object so massive that if it were placed at the center of our solar system, its event horizon would extend well beyond Pluto.
The accretion disk around it is so hot that it glows brilliantly in radio waves, and the black hole is shooting out a jet of particles at near light speed, a jet that extends for thousands of light years beyond the galaxy itself. This jet is visible across the electromagnetic spectrum, from radio waves to X-rays. The particles in the jet are moving at more than 99% the speed of light, accelerated to these extreme velocities by the intense magnetic fields near the black hole. The energy powering this jet comes from the gravitational potential energy of matter falling into the black hole, mass being converted to energy with an efficiency that makes nuclear fusion look wasteful by comparison.
If we could somehow slow down and orbit M87 safely, which would be impossible for many reasons, we'd see this jet as a brilliant stream of energized particles, driven by the rotation of the black hole and the magnetic fields threading through the accretion disk. It's one of the most energetic phenomena in the universe, powered by matter falling into an object from which nothing, not even light, can escape. The jet carries away enormous amounts of energy, heating the surrounding intergalactic gas and affecting star formation throughout the cluster. The Virgo cluster isn't just notable for M87, it contains numerous other remarkable galaxies. M49, another giant elliptical, is one of the brightest galaxies in the cluster. It's the first member of the Virgo cluster to be discovered, spotted by Charles Messier in 1771. M84 and M86 are large ellipticals located near the cluster's center, part of a substructure called Markarian's chain, a beautiful curved line of galaxies visible in telescopes, all gravitationally associated and falling toward the cluster's center. M87 itself is part of a smaller grouping within the cluster, demonstrating that even within galaxy clusters, galaxies form subgroups and chains. The Virgo cluster also contains several spiral galaxies, though these are less common in the cluster's dense core, where gravitational interactions tend to disrupt spiral structure. M58, M61, M88, M90, and M100 are prominent spirals in the cluster, their arms traced by young blue stars and pink star-forming regions. These galaxies have managed to retain their spiral structure despite the harsh cluster environment, though many are showing signs of ram pressure stripping, with their gas being swept back like hair in a strong wind as they move through the hot intercluster medium. As we pass through the Virgo cluster, we'd spend several hours traversing its core, given that the cluster spans roughly 15 million light-years. At our speed, that's 15 million seconds, about 174 days, or nearly 6 months. During that time, we'd pass thousands of galaxies, each containing billions of stars, each with its own population of planets, nebulae, star clusters, and all the other structures we've come to associate with galaxies. The sheer density of galaxies here is staggering. If we lived in a galaxy within the Virgo cluster's core, our night sky would be ablaze with the light of neighboring galaxies, dozens of them bright enough to cast shadows. 700 days in, 60.5 million light-years, we're still within the Virgo cluster's influence, passing through its outer regions. The density of galaxies is decreasing now, but we're still encountering more galaxies than we saw in the sparser regions before the cluster. At 800 days, 69 million light-years, we're finally emerging from the cluster proper, though we're still part of the larger structure it anchors, the Virgo supercluster, also known as the local supercluster. The Virgo supercluster is a vast structure containing at least 100 galaxy groups and clusters. It spans roughly 110 million light-years and contains perhaps 47,000 galaxies. Our local group is part of this supercluster, located on its outskirts, being slowly pulled toward the Virgo cluster's gravitational center.
This motion is superimposed on the expansion of the universe. We're simultaneously being pulled toward Virgo and carried away from more distant structures by cosmic expansion. Our local group is falling toward the Virgo cluster at about 400 kilometers per second, though it will never actually reach it, because cosmic expansion will ultimately win out, carrying us away faster than we can fall inward. At 900 days, about 2.5 years, or 77.8 million light-years, we're deep within the Virgo supercluster, but beyond the Virgo cluster itself. We're passing through regions containing other galaxy clusters and groups, all gravitationally bound in the supercluster's web. Some of these are substantial structures in their own right: the Fornax cluster, the Eridanus cluster, the Leo group, each containing dozens to hundreds of galaxies. At 1,000 days, we're at 86.4 million light-years. At 1,100 days, 95 million light-years. The structure of the Virgo supercluster becomes more apparent at this scale. It's not a spherical structure, but rather flattened, shaped like a pancake, with the Virgo cluster near one edge and our local group near the other. At about 1,273 days, roughly 3.5 years, we've traveled 110 million light-years. We're now at the far edge of the Virgo supercluster. Behind us lies a vast structure containing tens of thousands of galaxies, trillions upon trillions of stars, and incomprehensible numbers of planets. And ahead of us, the cosmic web stretches on, and we're about to discover that even superclusters aren't the largest structures in the universe. But before we continue, let's pause and reflect on what we've accomplished. In 3.5 years of travel at 1 light-year per second, we've crossed from our home in the local group, through numerous galaxy groups, through the massive Virgo cluster, and across the entire local supercluster. We've traversed a distance that light, traveling at its maximum speed, would take 110 million years to cover. And yet, we've barely scratched the surface of the observable universe. The distances that lie ahead are larger still, and the structures we'll encounter are more vast than anything we've seen so far. This is the point where the true scale of the universe becomes almost overwhelming. We've traveled 110 million light-years, a distance that light, traveling at its maximum speed, would take 110 million years to cover, and we've covered less than 0.1% of the observable universe's diameter. The cosmos is more expansive than human intuition can easily grasp, and we're about to venture even deeper into its immensity.
After 4 years, we've traveled 126 million light-years from Earth. We're now well beyond the Virgo supercluster, venturing into a region of space that reveals the universe's largest scale structure, the cosmic web. From our vantage point, if we could somehow see the distribution of galaxies across vast distances simultaneously, we'd observe an intricate pattern. Galaxies aren't distributed uniformly throughout space. Instead, they're organized into a web-like structure of filaments, sheets, and clusters, separated by enormous voids. Vast regions of space that contain very few galaxies at all. This structure emerged from tiny quantum fluctuations in the density of matter in the early universe. In the first moments after the Big Bang, space wasn't perfectly uniform. There were regions of slightly higher density and regions of slightly lower density. As the universe expanded and cooled, these density variations were amplified by gravity. Higher density regions attracted more matter, becoming denser still, while lower density regions lost matter to their denser neighbors, becoming voids. Over billions of years, this process created the cosmic web we see today. Dense regions collapsed into galaxy clusters and superclusters, connected by filaments of galaxies and dark matter. Between these structures lie voids, vast, empty regions that can span hundreds of millions of light-years.
At 150 million light-years, about 4.75 years into our journey, we're traveling through one of these transitional regions. We've left the Virgo supercluster behind, and we're crossing through a less dense region before encountering the next major structure. Galaxy groups still appear, but they're more dispersed, separated by larger distances than what we encountered within the supercluster. At 200 million light-years, about 6.5 years, we're approaching another major structure, the Hydra Centaurus supercluster. This is a massive concentration of galaxies lying in the direction of the constellations Hydra and Centaurus as seen from Earth. It's comparable in size to the Virgo supercluster, containing thousands of galaxies organized into multiple clusters. But there's something even more intriguing about this region. Beyond the Hydra Centaurus supercluster lies a structure that's been dubbed the Great Attractor, a gravitational anomaly that's pulling the Virgo supercluster, the Hydra Centaurus supercluster, and numerous other structures toward it. The Great Attractor itself appears to be centered on the Norma cluster, lying about 220 million light-years from Earth, but much of it is hidden behind the plane of the Milky Way, obscured by dust and stars in the foreground. We'd reach the Great Attractor region at about 220 million light-years, roughly 7 years into our journey. As we approach, we'd see a dense concentration of galaxies, evidence of the enormous mass concentration that's pulling on surrounding structures. But recent observations suggest that the Great Attractor itself might be influenced by an even larger structure farther out, the Shapley supercluster. At about 7.9 years, we're moving through regions containing numerous superclusters. The Shapley supercluster lies about 650 million light-years from Earth and is one of the most massive structures in the local universe, containing over 8,000 galaxies. It's so massive that it's the dominant gravitational influence on structures within 1 billion light-years, including our own local group. 300 million light-years in, which is 9.5 years into our journey, we're well into the cosmic web's structure. We're crossing through regions of high and low galaxy density, passing through the outskirts of various superclusters, and traversing the filaments that connect them. At this scale, individual galaxies become less significant than the overall pattern, the web-like distribution of matter that characterizes the large-scale structure of the universe. 400 million light-years in, we're encountering the Sloan Great Wall, one of the largest known structures in the universe. This is a vast sheet of galaxies stretching across more than 1 billion light-years, containing hundreds of thousands of galaxies. It was discovered through the Sloan Digital Sky Survey, one of the most ambitious astronomical surveys ever conducted, which mapped the positions and properties of millions of galaxies. The Sloan Great Wall isn't a solid structure in any conventional sense. It's a region where galaxies are more densely concentrated, forming a wall-like pattern in the three-dimensional distribution of galaxies. But even calling it a wall is somewhat misleading. It's more like a higher density region in the cosmic foam, a place where the web's filaments come together in a particularly prominent way. At 500 million light-years, about 15.8 years, we're beginning to traverse regions that are beginning to show the effects of cosmic expansion more prominently. The universe is expanding, and the farther we look, the faster objects appear to be receding from us. This is Hubble's law, the observation that galaxies' recessional velocities are proportional to their distance from us. It's not that galaxies are moving through space, rather, space itself is expanding, carrying galaxies along with it. At this distance, the light we see from galaxies left them 500 million years ago. That's during the Cambrian period on Earth, when complex life was just beginning to diversify in the oceans, when the first arthropods and early fish were evolving. The universe as we see it at this distance is younger by 500 million years than the universe around us now. 650 million light-years in, we'd be passing through the Shapley supercluster. This immense structure dominates the large-scale distribution of matter in this region. It contains over 20 galaxy clusters and has a total mass estimated at more than 10 quadrillion times the mass of the Sun. It's so massive that it noticeably affects the motion of galaxies over hundreds of millions of light-years. At 800 million light-years, about 24.5 years, we're in deep cosmological space. The structures we're passing are so distant that the light reaching Earth from them left during the Neo-Proterozoic era, when Earth was recovering from a series of severe ice ages, when multicellular life was just beginning to establish itself. At 1 billion light-years, 31.7 years into our journey, we're seeing the universe as it was when the first primitive animals were appearing on Earth. At this scale, the cosmic web structure remains evident, but we're also beginning to see the universe's overall homogeneity. On the very largest scales, over 1 billion light-years, the universe starts to look roughly the same in every direction. This is the cosmological principle in action. The idea that on sufficiently large scales, the universe is homogeneous and isotropic, meaning it has the same properties everywhere and looks the same in every direction. At about 47.5 years, we're traveling through a universe that's noticeably different from the one near Earth. At this distance, we're looking back to a time when the universe was about 12 billion years old, roughly 1.5 billion years younger than it is now. Galaxies at this distance appear slightly different, on average younger, with more active star formation, because we're seeing them as they were in the past. Just 2 billion light-years, 63.4 years into our journey, we're at distances where cosmic expansion becomes a significant factor in our observations from Earth. Galaxies at this distance are receding from us at significant fractions of the speed of light due to the expansion of space itself. Their light is substantially redshifted, stretched to longer, redder wavelengths by the expansion of space between the time the light was emitted and when it reaches observers. At 3 billion light-years, 95 years into our journey, we're seeing the universe as it was when it was about 10.8 billion years old. This is still relatively recent in cosmic history, but we're starting to see differences. The rate of star formation in the universe was higher in the past than it is today. 3 billion years ago, more galaxies were actively forming stars, and the universe was on average brighter and bluer than it is in the present day. This marks our transition into the next phase of our journey. We've crossed through the local universe, through the cosmic web's intricate structure, and we're now venturing into deep cosmic time. The farther we travel, the farther back in time we're looking, and the more dramatically different the universe becomes. This is where we begin to see the universe's evolution, where we witness galaxies at different stages of their development, where we observe the cosmos transforming from the young, energetic universe of the past into the mature,
quieter universe we inhabit today. At 4 billion light-years, 126.82 years so far, we're traveling through a universe that's beginning to look noticeably different from our local cosmic neighborhood. We're seeing galaxies as they appeared when the universe was about 9.8 billion years old, roughly 70% of its current age. At this epoch, the rate of star formation across the universe was near its peak, This was a time when galaxies were actively building up their stellar populations, when massive stars were being born in great numbers, and when the universe was blazingly bright with young, hot stars. The galaxies we're passing at this distance show evidence of this vigorous activity. Many are undergoing major bursts of star formation, triggered by galaxy mergers or by abundant supplies of cold gas falling into their centers. We'd see more irregular galaxies here than in our local neighborhood, galaxies that haven't yet settled into the neat spiral or elliptical forms that terminate the present-day universe. Approximately 5 billion light-years, 158.5 years, we're looking back to when the universe was about 8.8 billion years old. This is roughly the time when our own sun formed. The solar system came into being at a time when the universe was already quite mature, when most of the current generation of stars had already formed, but when star formation was still more vigorous than it is today. 6 billion light-years so far, 190 years, we're at a look-back time of about 6 billion years. The universe was about 7.8 billion years old. This is a transitional period in cosmic history. The peak era of star formation was beginning to decline. Galaxies were maturing. Many of the massive elliptical galaxies we see in the present day had already formed through mergers of smaller galaxies. The universe was beginning its long, slow transition from the star formation-dominated era to the quieter, more sedate universe we observe locally. At 7 billion light-years, about 222 years into our journey, we're looking back to when the universe was about 6.8 billion years old, roughly half its current age. This is a significant milestone. At this distance, we're looking back to an era when the universe's expansion was beginning to accelerate. For most of cosmic history, the expansion of the universe was slowing down, decelerated by the mutual gravitational attraction of all the matter it contains. But about 5 to 6 billion years ago, a mysterious force began to dominate, a force we call dark energy. Dark energy is perhaps the deepest mystery in modern cosmology. It appears to be a property of space itself, a kind of negative pressure that pushes space apart, accelerating the expansion of the universe. We don't know what dark energy is. We don't know why it exists or what determines its strength, but we know it's real because we can observe its effects. The universe's expansion is accelerating, and dark energy is the name we give to whatever's causing that acceleration. After 8 billion light-years, 253.6 years into our journey, we're looking back 8 billion years to when the universe was about 5.8 billion years old. At this epoch, dark energy was just beginning to dominate over matter. Before this time, the universe's expansion was decelerating. After this time, it was accelerating. This transition point marks a fundamental shift in the universe's evolution. At 9 billion light-years, 285.3 years into our journey, we're seeing galaxies that formed relatively early in cosmic history. Many of these galaxies were already well established by this time, having formed their first generations of stars billions of years earlier. But we're also seeing many galaxies in the process of assembling, small galaxies merging to form larger ones, dwarf galaxies being accreted by more massive neighbors. After 10 billion light-years, 317 years into our journey, we're looking back to when the universe was about 3.8 billion years old, less than 30% of its current age. This is getting into the era of early galaxy formation.
The first galaxies formed only a few 100 million years after the Big Bang, but they were small, dwarf galaxies containing perhaps millions to tens of millions of stars. Over time, these small galaxies merged to form larger ones, building up the galaxy populations we see today through a hierarchical process of assembly. At this distance, we're seeing many of these early mergers in progress. The universe at this epoch was denser than it is today. Space has expanded significantly since then, and galaxies were closer together, making interactions and mergers more common. The galaxy population looks different here. Smaller galaxies are more numerous, irregular morphologies are common, and many galaxies show signs of recent or ongoing mergers.
Now, 11 billion light-years in, 348.7 years, we're seeing the universe at about 2.8 billion years after the Big Bang. We're now in the era when many of today's massive galaxies were in their formative stages. The supermassive black holes at the centers of galaxies were growing rapidly, fed by abundant gas falling into galactic centers. This was the era of quasars, extremely luminous objects powered by matter falling into supermassive black holes. Quasars are among the most luminous objects in the universe. A single quasar can outshine an entire galaxy, emitting more energy than 100 billion suns, all from a region no larger than our solar system. This energy comes from the gravitational potential energy of matter falling into the black hole, heated to millions of degrees and radiating across the electromagnetic spectrum. Quasars were much more common in the early universe than they are today, suggesting that supermassive black holes were growing more rapidly in the past. At 12 billion light-years, 380.4 years into our journey, we're seeing the universe at about 1.8 billion years after the Big Bang. This is early in cosmic history, but it's not the beginning. The first stars had already formed, lived their brief lives, and exploded as supernovae, seeding the universe with heavy elements. The first galaxies had assembled from smaller building blocks, but we're still in an era when the universe was fundamentally different from today. At this epoch, the universe was smaller, denser, and hotter. The cosmic microwave background, the afterglow of the Big Bang, had a temperature of about 10 Kelvin compared to its current temperature of 2.7 Kelvin. That might not seem like much of a difference, but it's significant on cosmic scales. The universe was filled with more radiation, and the conditions for star formation were different from what we observe in nearby galaxies. At 13 billion light-years, 428 years into our journey, we're looking back to about 800 million years after the Big Bang. We're now in the era of the first galaxies. These early galaxies were small and irregular, nothing like the majestic spirals and ellipticals we see in the nearby universe. They were intensely star-forming, building up their stellar populations rapidly from the primordial gas that filled the early universe. This era is sometimes called the Cosmic Dawn, the period when the first galaxies formed and began to illuminate the universe. Before this time, the universe had gone through a period called the Dark Ages, after the cosmic microwave background formed, but before the first stars ignited. During the Dark Ages, the universe was filled with neutral hydrogen gas, cold and dark, with no sources of light except the fading afterglow of the Big Bang itself. The first stars and galaxies ended the Dark Ages through a process called reionization. The intense ultraviolet radiation of young, massive stars began to ionize the neutral hydrogen in the intergalactic medium, stripping electrons from hydrogen atoms and creating bubbles of ionized gas around early galaxies.
Over hundreds of millions of years, these bubbles grew and merged until the entire universe was reionized. 13.5 billion light-years in, 428 years into our journey, we're seeing the universe at about 300 million years after the Big Bang. We're now at the limits of what current telescopes can observe. The James Webb Telescope, launched in 2021 and beginning operations in 2022, was specifically designed to observe this era. Its infrared capabilities allow it to see the light from early galaxies, heavily redshifted by cosmic expansion into the infrared portion of the spectrum. At this distance, we're seeing some of the first galaxies that ever formed. These are the ancestors of all galaxies that exist today, the building blocks from which the cosmic web assembled. They're small, compact, and incredibly distant, appearing as faint smudges even to our most powerful telescopes. But they're fundamentally important for understanding how the universe evolved from the nearly uniform state we see in the cosmic microwave background to the rich structure we observe in the nearby universe. After 13.7 billion light-years, 434 years into our journey, we're approaching the practical limits of galaxy observation. Beyond this distance, galaxies become so faint and so heavily redshifted that detecting them requires extraordinary effort. But we're not yet at the edge of the observable universe. That lies farther still, not defined by the limits of our telescopes, but by the fundamental structure of space-time itself. And that's where we're heading next, toward the cosmic horizon, the edge beyond which we cannot see.
At 14 billion light-years, 443.7 years into our journey, we're traveling through a region of space-time that's becoming increasingly abstract. We're so far from Earth, looking back so far in time, that the universe we're observing barely resembles the cosmos we know. The galaxies here, if we can still call them that, are primitive structures, the first collections of stars to coalesce from the primordial gas that filled the early universe. They're small, irregular, chaotic, nothing like the majestic spirals and ellipticals that populate the universe today. These are the building blocks from which all later galaxies would form, the seeds of cosmic structure. But we need to clarify something important about distance at this scale. When we say we're 14 billion light-years from Earth, what do we mean? The light from objects at this distance left them 14 billion years ago, traveling through space that was expanding as the light traveled. The actual current proper distance, the distance if we could somehow freeze the expansion of the universe and measure the distance right now, is much larger, perhaps 30 billion light-years or more. The expansion of space itself has carried these early galaxies farther away while their light was traveling toward us. This distinction matters because it highlights a fundamental feature of cosmology. In an expanding universe, distance and time become intimately connected. When we look at distant objects, we're not just seeing them as they are far away, we're seeing them as they were in the distant past. The farther we look, the farther back in time we see, until we reach a point where we're looking back to the very beginning of the observable universe itself. Cosmology is, in this sense, a form of time travel. We're witnessing the universe's history written across the sky. At 14.5 billion light-years, we're seeing the universe at about 200 to 250 million years after the Big Bang. This is the very edge of the epoch of reionization, when the first stars and galaxies were beginning to ionize the neutral hydrogen that filled intergalactic space.
The objects we're seeing here are among the very first luminous structures to form in the universe. They're faint, distant, and incredibly difficult to observe from Earth, even with our most powerful telescopes. But they're crucial for understanding how the universe transitioned from the smooth, nearly featureless state we see in the cosmic microwave background to the richly structured cosmos today. These early galaxies are fundamentally different from modern galaxies. They formed from gas that had a different composition, almost entirely hydrogen and helium, with only trace amounts of heavier elements produced in the Big Bang itself. The lack of heavy elements had profound consequences for star formation. In modern star-forming clouds, elements like carbon and oxygen help cool the gas by radiating away energy, allowing clouds to collapse and fragment into individual stars. Without these cooling agents, the first star-forming clouds remained hotter and collapsed into more massive objects. The first stars, called population 3 stars, were likely much massive than typical stars today, because the absence of heavy elements meant that star-forming clouds couldn't cool as efficiently, leading to the formation of more massive stars. Population 3 stars would have been extraordinary objects, perhaps 100 or even 1,000 times the mass of the Sun, burning through their nuclear fuel in just a few million years before exploding as supernovae or collapsing directly into black holes. These explosions would have seeded the early universe with the first heavy elements, carbon, oxygen, iron, and all the other elements necessary for planets and life, making possible the formation of population 2 stars, stars with small amounts of heavy elements, and eventually population 1 stars like our Sun. At 15 billion light-years, 475.2 years into our journey, we're at about 150 million years after the Big Bang, potentially seeing some of the very first stars igniting. The universe at this epoch was a different place. It was smaller, denser, hotter. The cosmic microwave background, now cooled to 2.7 Kelvin, had a temperature of about 20 Kelvin. The rate of cosmic expansion was faster than it is today, and the first glimmers of light were beginning to pierce the cosmic dark ages. But this is near the edge of what's theoretically observable with galaxies. Before about 100 to 200 million years after the Big Bang, there were no stars. The universe was dark, filled only with cooling gas and the fading radiation from the Big Bang itself. This period is called the Dark Ages, and it lasted for perhaps 100 million years, a substantial fraction of the universe's early history. However, the observable universe extends beyond the epoch of the first stars. There's something we can still observe from even earlier times: the cosmic microwave background. This is radiation that was emitted about 380,000 years after the Big Bang, when the universe cooled enough for neutral atoms to form for the first time. Before this moment, called recombination, the universe was filled with a hot, dense plasma of electrons and protons. Photons couldn't travel far in this plasma before being scattered by free electrons, making the universe opaque to light. It was like trying to see through fog. Light couldn't propagate freely. At about 46.5 billion light-years proper distance, the current edge of the observable universe, we've reached the cosmic horizon. This is as far as light could have traveled since the Big Bang, given the expansion of the universe. Beyond this horizon, there's almost certainly more universe, possibly infinitely more, but it's fundamentally unobservable from our location in spacetime. The light from regions beyond this horizon hasn't had time to reach us yet. As the universe ages, the observable universe grows, encompassing regions that were previously beyond our cosmic horizon. At our speed of 1 light-year per second, reaching this point from Earth would take about 46.5 billion seconds. That's roughly 1,475 years. But remember, this is the proper distance, the distance accounting for the expansion of space. The light travel time is shorter, about 13.8 billion years, which we'd cover in about 437 years at our impossible speed. So let's say we've reached this point, 437 years into our journey at the edge of the observable universe. What would we see? Paradoxically, nothing. We've traveled so far that we've reached the epoch before galaxies formed, before stars ignited, before any luminous objects existed. We're at the edge of the dark ages, surrounded by cooling hydrogen gas and the omnipresent glow of the cosmic microwave background, now blue-shifted back toward visible wavelengths by our motion through spacetime. And this is where our impossible journey must end, not because we lack the will to continue, but because there's nothing more to see.
But what if we turned around? What if, having reached the edge of the observable universe, we reversed course and began the long journey back to Earth? The return trip would take another 437 years at our impossible speed, and it would reveal something profound about the nature of time and the evolution of the cosmos. As we journey back toward Earth, we're not simply retracing our steps. We're traveling forward through cosmic time. The universe we see around us during our return journey is not the same universe we observed on our outward voyage. It's older, more evolved, transformed by 437 years of continued expansion and development. But more importantly, we're seeing different epochs of cosmic history as we approach regions progressively closer to our own time. As we pass back through the regions we traversed on our outward journey, we might notice something else. The universe is not static. Galaxies we passed months or years ago have continued their inexorable dance. Binary galaxies we saw approaching each other have moved closer, perhaps already merged. Galaxy clusters we passed through have continued to accrete new members. The cosmic web we traced has evolved, though on timescales so vast that even our impossible 437-year journey represents just a blink in cosmic time. Consider the Virgo cluster, which we'd reach again about 188 years into our return journey. The cluster we observe now has had nearly 900 years to evolve since we first passed through it, 900 years during which galaxies have continued to fall into the cluster, during which ram pressure stripping has transformed more spiral galaxies into red ellipticals, during which the intra-cluster gas has been further heated by supernova explosions and active galactic nuclei. The changes would be subtle, invisible to casual observation, but they'd be there, the cluster slowly growing more massive, more relaxed, more evolved. The local group, which we'd reach about 430 years into our return journey, just 7 years before arriving home, would show similar subtle changes. Andromeda and the Milky Way, those two great spirals falling toward each other, would be measurably closer together than when we left, though still millions of years from their eventual merger. The dwarf galaxies orbiting both would have shifted in their positions. Some might have been tidally disrupted, their stars scattered into streams. Others might have fallen closer to their parent galaxies, beginning the slow process of being absorbed. And what of Earth? What would we find when we finally returned home 874 years after departing on our impossible journey? Nearly 9 centuries would have passed. Empires would have risen and fallen. Technologies we can't imagine would have been invented, used, and perhaps discarded. Humanity itself might have changed in ways we can't predict, perhaps spreading to other stars, perhaps transforming through genetic engineering or technological augmentation, perhaps achieving things that today seem like fantasy. Or perhaps, and this is the sobering possibility, we'd find silence. 9 centuries is a long time in human history. Civilizations have collapsed in far less time. The Earth we return to might be very different from the one we left, transformed by climate change, nuclear war, pandemic, or challenges we haven't yet imagined. Or it might be unrecognizable in a positive sense, transformed into something beyond our current comprehension. Our impossible journey ends where it began, on Earth, that small blue world in the outer suburbs of the Milky Way. But we return transformed by perspective, by the recognition of our true place in the cosmos. We're small, yes, infinitesimally small compared to the vast reaches of space we've traversed, but we're also profound. We are the universe's way of knowing itself, and that makes us, in our own way, as significant as any galaxy, any cluster, any structure in the cosmic web. The journey may be impossible, but the wonder it inspires is real, and perhaps that's enough.